See when? Okay. Good morning, everyone. This is our May EM-X symposium, and we have two great speakers again. One biology and one physical sciences, and one is an American who's working in the UK, and the other is a UK person working in America. So we'll be very happy to hear from them. I'm just say a little bit about Peter, who's past president and worked so hard for the Microscopy Society of America, which we really appreciate all your efforts, Peter. And you become the voice of America, as it were, here, because you always announce the awards. And so everyone not only loves to listen to your voice, they like to get the awards as well. So that's you're one of the most popular people in MSA, I should say, as a consequence. Anyway, I'll pass it on to Wah to introduce Chris. Wah, please.
Okay. All right. Good morning. I'd like to welcome everyone to come our monthly EM-X symposium of Stanford. And this morning we are delighted to have Christopher Russo to give us his progress. Chris was trained at Harvard Physics, and then he went to do postdoc with Richard Henderson's and at the Laboratory Molecular Biology and Medical Research Councils. And he has done some really remarkable research in the last few years, even during the pandemic time. And he was just tenured to be a group leader at the LMB MRC in Cambridge. And he had done numerous pioneering work from specimen preparations to how to get the best, every last little juice from the electrons for the images. And he has numerous patents. Apparently he's a very creative guy. And then his accomplishment has been recognized, and he received the very prestigious Burton award from the MSA a couple of years ago. And today he will address the questions of molecular structure determination extrapolate to zero dose with an electron cryo microscope. And Chris, thanks very much for joining us this morning.
Great. Thanks very much, Wah. And thanks to Bob and the other organizers for inviting me. We're huge fans of these talks here in Cambridge. Lots of us watch them. And not just because there's biology talks, but in fact, because there's non-biology talks, because we often get lots of ideas and learn lots of new things by, standing at the interface between fields. I've been doing that for a long time in my career. And I think it's a terribly good thing to have, lots of interaction between our areas, even though, we have a common interest in electron microscopes. What we do with them often seems to diverge, but I think there's more overlap than most people think. And so today, instead of sort of giving you an overview of all the things that we've been working on, I'm going to go into one problem in detail, which I think is quite exciting in our field. And, I've benefited hugely from the developments in material science and metallurgy and in physics in my work on biological specimens for electron microscopy. And I'm now offering this as sort of my idea to give back to the material science community, because I have no doubt that it will have some interest to you all as well. And I think, as I said, the interchange between our fields is very powerful. Right, so with that, I'm going to get started here, hopefully. There we go. So just a quick reminder, in cryo-EM in biology, the mainstay of our field is to take low-dose images of a protein or nucleic acid specimen, molecules that are in complexes. You can see here, these are ADS ribosomes on a sheet of graphene. And this is a bright field phase contrast image, which has about 16 electrons per angstrom squared in it. And so we take lots of images like this. And from these images, there's enough contrast in each one of these individual particles that we can align the individual particle images with each other, creating a much higher resolution image, if you will, in 2 dimensions and ultimately in 3 dimensions, which then gives us a 3-dimensional map, which allows us to determine the position of every single atom in all of this, amazingly complicated structure. This ribosome is something like 300 angstroms across. It has something like 300,000 atoms in it, and you can precisely place every single one of them in the map for this. So this, of course, is the triumph of electron microscopy in biology, is the fact that we can now do this successfully and repeatedly. And but I thought I would just show a quick video of what it's like to be one of these molecules in the electron microscope. I'll just play it one more time for fun. The reason we use such low dose is because the electron beam completely destroys the molecules, breaks every single bond in them. And this form of radiation damage, which they're subject to in the electron microscope, is really devastating. And that's why we have to rely on this trick of averaging lots of images together. But even before they're damaged, there's lots of interesting things going on, and interesting, it turns out, physics problems. And this is what I've been studying for some time now. So this is a slide that I put together for a review we were writing recently. It just sort of shows you how successful this technique is these days. So what I'm showing you on the screen here is all of the structures, atomic resolution structures, that were deposited in the map in 1 week in February. They were deposited in the EMDB with their atomic models in the PDB. And you can see there's a variety of different specimens, from very small to very large, to filaments, to helical. All of these are now being deposited with great regularity in the EMDB. And we're in this exponential growth phase, without a doubt. And this started with the advent of direct electron detectors, but has had contributions from lots of different areas of technology, including improvements in specimen preparation, improvements in the software that's used to actually do these reconstructions and average the images together and create the 3D maps. There's been improvements in modeling into the maps that are generated. So all of these things are now contributing to this exponential growth, but we don't want to stop here, right? We want to keep going with this exponential growth, because there are lots more structures that need to be solved, and lots more that we will want to do in the future. So one major problem that was holding back the field for quite some time, and it was realized very early on that this was a problem, but all the details of it were not entirely appreciated until we started exploring it very carefully. And in many ways, the direct electron detectors were the key piece of technology that allowed us to work all this out, because we were able to take movies of the specimens in time. And so the problem is specimen movement, or specimen motion, and it happens at several different length scales. So this slide is just summarizing the length scales over which specimen movement occurs. And there's sort of the earliest or most well-recognized form of specimen drift that was recognized the earliest on, which is stage drift. So if you have a specimen at cryo temperatures and it's being cooled by a copper rod, and that copper rod changes in temperature by a fraction of a degree, you get tens of angstroms of change in the length of the rod, and therefore you get drift of the specimen. And so this is sort of a boring form of drift, but it was one that was solved earliest on with careful design of the cryo specimen holders. And then about 10 years ago now, almost, we realized that actually there was another form of specimen movement that was caused by the differential contraction of the foil, which was suspended across the normal cryo-EM grid that we would use. So you had a metal grid and you had a carbon foil suspended across it, and the differential contraction of those two during preparation caused it to crinkle up and led to instability in the specimen. And so by making the grid and the foil out of one material, in this case gold, you eliminated this form of differential contraction and eliminated the movement that was caused by it. And that was basically what's being summarized here. This is the RMS displacement of a whole ensemble of particles like those ribosomes you saw on the first slide. And they moved anywhere from 0 to 5, 10, even more angstroms. And as we kept trying to develop better and better specimen supports, we reached on this idea that the foil was causing a lot of it. So we got down to about 2 angstroms, and this was back in 2014 and shown again in 2016. So this was good, but it wasn't quite there yet. And that's because not all of the movement was removed. So the movie you saw there was showing the difference in the foil movement. But when you track gold nanoparticles in thin layers of ice within the hole here, you can see that even if the edge of the foil is completely motionless to better than an angstrom, you can see the lattice right in the foil, the particles inside the foil are actually moving. And not only that, they're moving in a correlated way. It's not like they're randomly moving in different directions. The whole piece of ice is moving. And this was a mystery that we needed to solve. And so we dug into it in great detail to try and solve it. And then if you were to go even further in looking at movement in the specimen, you reach the point at which the water molecules are actually moving during irradiation in the beam. And this was, it was worked out as well by Greg McMullen in about 2015. And it turns out that they're not moving too much. They're moving about an angstrom per electron per angstrom squared. And that also will impart a movement to any particle that's embedded in an ice layer like this, but it'll be a random movement because all of the water molecules are moving randomly relative to each other. So they induce a pseudo-Brownian movement of each of those particles. And then of course, there's the thermal vibrations of the atoms and their bonds. And for the purposes of cryo-EM and building models of molecules, we can neglect this. So how do we get from here, which is where we were in about 2014, down to here? Well, we tried adding graphene to these, and that did help, but it still didn't bring us all the way down to this theoretical limit set by the diffusion of the molecules. And so one thing you can do is, of course, use movement tracking software. And there's been an increasing both number and sophistication of algorithms that have been published and developed in order to try and track the movement of the particles and then compensate for it in post. So you take a movie and then you try and compensate for the movement of the particle in the image in the movie. And the part of this is a success story, but also part of it is a failure story, because if any of these were perfect, then we wouldn't need to do any more and everybody would be using them. But unfortunately, none of them actually bring back all of the information. So they all work, but that none of them work well enough to bring back absolutely every bit of information, particularly at the beginning of irradiation. And how do we know this? Well, we know this because there have been lots of studies of the damage to molecules using X-ray crystallography at the same temperatures that we use for our cryo-EM. And in all of these, you can see that the information, in this case characterized by a B factor, or Debye-Waller temperature factor, which is basically how far out the atom is blurred from its original position, this is entirely linear all the way back to extremely low doses. So if you translate this to electrons per angstrom squared, even in the very first electron per angstrom squared, this should be perfectly linear in decay. And the mechanisms of radiation damage in X-ray are essentially the same as they are in the electron microscope. So this is what we would expect if there really was no movement. And in cryo-EM, even in the best high-resolution structures from using all of the best motion correction algorithms, we still cannot get this. The first frame is always worse, or at best about the same as subsequent frames at around 4 or 5 electrons per angstrom squared. So you always see this phenomenon where there's a maximum and then it starts to decay like you might expect from radiation damage. And but what we would want to have is a linear decay starting absolutely from 0 dose in order to be certain that the first frame, first of all, is the best, and that now we have no motion that is actually blurring the information in the image. So what can be done? Well, our approach to this was to very carefully study the movement of those gold nanoparticles that I showed you in that first image in lots of different holes and lots of different substrates. And after many experiments, a pattern began to emerge. And in fact, a very interesting pattern began to emerge. And that was to say that by reducing the size of the hole that the ice layer is suspended across, the movement is reduced. But actually, after the hole was reduced to below a size of about 0.3 microns, 300 nanometers, there was no further reduction in the movement of the particles. So there was actually a threshold effect. So once one made a hole that was small enough, eventually the particles stopped moving entirely. And if you kept making the hole size smaller and smaller, it didn't change the movement of the particles anymore. So this is interesting, of course, because this means there's some real physics going on here. And this is true. You can exaggerate the effect by tilting the specimen to 30 degrees, because most of the movement that we see is actually in plane, and it's due to buckling. And so what this suggested is that there was actually a buckling phenomenon coming up, involved in the creation of these movements that we were seeing. And so we tried to work out exactly the details of how one might explain this. And so here's our theory of this buckling. And essentially, it's a simple thin film mechanics problem. If you have a stiff material suspended across a hole and you apply a normal force to the edges, at what point does the strain get so high that you actually buckle the material in order to relieve it? And it depends, of course, on the Young's modulus of the material and the Poisson's ratio. And there is some critical number above which this material will actually buckle. And so we calculated this for the frozen amorphous water ice that we have in our holes. And it turns out that there's actually a critical aspect ratio as well. So if the height divided by the width of the thin film is greater than about 10, then the stress that's in the force that's induced by reducing the temperature of this water during freezing is sufficient to actually cause it to buckle. And if not, it doesn't. And so this phase diagram is our way of actually sort of explaining what's going on here. So you start out with your liquid water at 4 degrees C, and then as you cool it down during a cryoplunging specimen preparation, it gets colder and colder, and eventually you reach the homogeneous nucleation point, which is starred here. So this is the point at which the water actually becomes solid and starts to build up stress. Up until this point, there is no stress built up because it's still a liquid. So it cannot withstand any normal force. It just gets smaller. But here is where you start to build up stress. And then the stress builds up enough that it actually exceeds this critical threshold and buckles. So the buckling event actually happens not while you're imaging it in the microscope. It happens while you're making the grid, while you're actually plunging the grid. And then the stress that builds up after the buckling event releases it is then the difference between the density here and the density that you finally end up at when you go all the way down to 100 Kelvin or so. And then when you put the specimen in the microscope, so this is this buckling event that happens here. And then when you put the specimen in the microscope, that pseudo diffusion of water molecules that I showed you at the beginning, that actually allows the water to move around on the specimen. And therefore, the strain that's caused during this cooling phase here is released because the water molecules are allowed to move again. And that's what we see as movement in the electron microscope. That's the movement that happens in the first phase. So it's an additional buckle, if you will, or bending that is releasing the strain built up during the specimen plunging process. So this was quite a surprise for us, and it's obviously not a simple thing. And it explains why it was such a tricky thing to work out in the end. But the good news is, now that we have a proper theory of what's going on here, we can actually do something about it. So these are the commercially available foil hole sizes that you would normally buy from, say, Quantafoil or C-Flat or some other company. And they are all in the regime where things are unstable because the specimen is only, say, 300 angstroms thick, but the hole size is much larger than 10 times that, right? And so only when you get down into this range do you actually end up in the regime where there is no buckling during the plunge. But this is where we wanted to be. So, but you could, of course, make a thicker layer of ice and then have stability even in a larger size hole. And we've seen that as well. But for single particle cryo-EM, where most of our specimens are around 200 or 300 angstroms thick, then it was very clear that we needed to have smaller holes in order to take advantage of this lack of buckling during plunging. And so here's what one of these holes looks like. So this is about 300 nanometers across, and it has a nice protein specimen embedded in it. And if you track the particle position of every single one of these particles within the hole during a typical image, so here's going all the way out to 30 electrons per angstrom squared, you see none of the particles move by more than an angstrom. So this is And you can see they're also linear in mean squared displacement. So this really shows, first of all, that the movements of these particles is all now uncorrelated. So now it really is not some bending or movement of the ice layer. And it should track beautifully according to how much we think the water molecules are moving themselves and causing this random pseudo diffusion of the particles. So all of this then lined up together. So we were pretty confident that we're on solid ground now. So we introduced these a couple of years ago now and gave them a name called a hexafoil. And I'll show you, of course, why in a minute we call them that. And they indeed did bring us down to this pseudo diffusion limit that we expected could be achieved if we completely eliminated the movement of the ice layer itself. But of course, there's a problem in cryo-EM. Well, there's a problem in the world, many problems in the world, one of which is a lack of fuel. Sometimes that becomes acute here in the UK, but there's also an acute lack of grids in the world. Time recently, I went and checked how many grids we had on back order in the lab, and it was more than 10,000 for months. So this is a serious problem. I mean, we can't have the whole field of cryo-EM held back by availability of grids. So we thought, now that we had a design for a grid that really was going to be optimal, we should do something about the supply problem as well. So how do we make a grid that both solves this problem of movement and scales with demand? So we turned to the semiconductor manufacturing industry, and it's lots of methods that have been developed over many years. And we came up with a wafer scale process where we can actually manufacture the entire grid and foil for the specimen support on a 4-inch wafer. And this is one of the first ones we did fully successfully, which we took a picture of. And you can see there's several hundred grids here, close to not quite 1,000 on a 4-inch wafer. And you can do this on a 6-inch wafer or an 8-inch wafer, as big as you like. But we did all of this here in the lab. And this is the process. I won't go through it in too much detail, but we just recently published this in ultramicroscopy. And I wanted to make sure that, there was this phenomenon where, there are so many grids made by so many commercial manufacturers that we actually lost the ability to make these grids ourselves, right? And they've been so successful, it's sort of was a bit frustrating because all people are able to make in the lab are the foils that you put on top of a grid, but we wanted to be able to do the whole thing and have control over the grid bar size, the grid bar pattern, spacing, as well as the foil hole size and pattern and spacing. And so we developed this sort of integrated process, which puts it all together. It involves a couple of mask steps, but in the end is quite straightforward to do. And in the end, you start with the silicon wafer and raw materials, and in the end, you have a dish of 1,000 grids ready to be used. So I'll just highlight two pieces of this lithography process that were somewhat unusual relative to sort of standard wafer processing techniques. One of them was using phase interference lithography. So to make holes smaller than the wavelength that you were using for your typical mask aligner system, that's not so easy to do, but there is this technique that uses phase interference lithography and a variable distance between the wafer and the mask to increase the effective resolution of the mask such that we could make 200 or 300 nanometer holes, even using a mask that had much less fine spacing than that. It's called Talbot interference lithography, which was developed for other things, but we took advantage of it here. And then the other key thing that we had to develop was a way to make thin foils of gold that were that had crystals that were smaller, because if you put a thin layer of gold down in a typical evaporation, you end up with crystals that are of order hundreds of nanometers in size. And so this was not sufficient to make nice, small, round holes, which we wanted to put these specimens in. So we developed an evaporator that had a cryostage, allowing us to reduce the grain size of the gold crystals by an order of magnitude or more. And then that allowed us to make these very nice round holes for the specimen. So now that we have these grids, what can we do now that we have complete control over grid manufacturing? Well, it really is a blank sheet of paper now. we can make the grid look like anything you want. You can literally draw it on, a piece of paper or, Illustrator, or in our case, in a CAD program, and you can have that as your grid. It can be any size, it can be any shape. The grid bars can have any, thing within the limits of the lithography process and the processes we're using. So a few things that we added to the grids that we wanted to have were fiducial marks that allow us to track our position on the grid. Things that you could see by eye when you're holding them with a pair of tweezers, as well as in an electron microscope or even at high resolution. You can put fiducials, you could put barcodes, you could put numbers, anything you like here in principle, and then actually figure out where you are in the various steps of specimen preparation. So I think this is going to be useful to people. We actually put all of these masks online as a supplemental material in the paper. So anybody who wants to try and do this themselves, I would say most biochemistry labs aren't going to have the equipment to do it, but material scientists certainly may have access to lots of facilities that could, do these sort of things. So please do have a look. We really did publish absolutely everything in this process. And here's what it looks like when you actually take them in the electron microscope. So one of the other bottlenecks in cryo-EM these days is actually having enough good holes to image. The detectors are so fast and the microscopes are so fast that you can image thousands of holes per hour now. And so feeding the microscope enough good holes to look at turns out to be a limiting factor. But now we have increased the density of these by another factor of 10. So now each hexagon in this case, not square, has more than 5,000 holes. So you can get a complete data set from a single hexagon, whereas, on a typical grid, you would only have about a couple hundred holes here. So we did commercialize this, and hopefully these are going to be available soon from SPT LabTech and Quantifoil. Right, so in terms of structure determination, what can we do now that we could never do before? Well, the first thing that we can do is actually use the first electron per angstrom squared. So this is just showing an atomic model of a couple of side chains here, and the corresponding map reconstructed from each frame all the way out to 30 electrons per angstrom squared. And you can see here by 20 or 30, the side chains are completely destroyed. But as you come back up here, the water molecule shows up and all the density for the side chain comes back. And now the first electron per angstrom squared really is the best map. This is the best one, and you want this one. Whereas, all of the programs previously were basically throwing this away one way or another, either down weighting it or actually even omitting it. But there's something else we can do now that we have a proper physical model for both the movement of the specimen and for radiation damage of the specimen. And that is go back to before the first electron per angstrom squared. So actually reach back in time to before the electron microscope was turned on. So how do we do this? And you can see this is even better. Well, the idea is, let me just show you one more video here of data, and just to try and convince you that this really is real and important. So this is a very high resolution structure of aproferritin that was determined on an ultrafoil grid. So an all gold grid, our previous generation ones, but with a larger hole size. And this is one of these really high resolution, 1.2, 1.3 angstrom kind of deals. But you can see in the first 0.1 electrons per angstrom squared, the density actually doesn't look so good. And then as you progress to about 2 or 3 angstroms per electron squared, it improves. And then eventually it decays again, as you might expect. So even in the very high resolution apoferritin structures that have been published, there is radiation damage incorporated, and the early frames are actually significantly worse. That's what's characterized here. So if we look at the same thing on one of these hexafoil supports where the movement is eliminated, you find that the first electron per angstrom squared is the best still. And you can see that in all the little features in the map, the water molecules, the side chains, the ions, and it gets progressively worse. So, you end up with a curve that looks like this. So, having a high resolution map is not a solution to radiation damage. It does give you more features in the map, but they may not necessarily be features of an undamaged molecule. So what can we do to do this extrapolation business? Well, the idea is that we take all of the amplitudes and phases measured in the map. And since we have all of them measured at all time points, which is something we never had with crystallography, where this has been done previously, we have both the amplitudes and phases, we can take these structure factors and extrapolate them back to 0 dose. And we do that by a very simple fitting. And instead of taking a dose-weighted average of each one of these frames, which is what's done now, we can actually use all of the information from fitting all of these parameters to figure out the position here at 0 dose as accurately as possible. So, as this is just sort of a little graphical illustration of that, you work your way back up the dose to the beginning, and then your final map is actually the best interpretation possible of what the molecule was like before you even turned on the electron beam. And this is what this actually looks like for some particular structure factors. This is an amplitude fit and a phase fit. And so this is what actually goes into the final map that you go and build your model into. So one way to think about this is if you're fond of phasors, or thinking in sort of real and imaginary parts of complex numbers, what we're trying to do here is determine the trajectory of this complex number as a function of fluence. And we actually map that back to 0. And you can do this using imaginary and real, or amplitudes and phases, however you like. But in the end, you try and go back here to 0 with as accurate a fit as possible. So we're working on, what's the best way to do this right now. The basic idea is that we can actually rewind this movie back to the point where there is absolutely no damage to the thing you're interested in looking at. So what does this actually look like in practice? We've now done this with quite a few structures since we've had these grids for a while now. So the data collection is just like normal. So you go collect your movies, lots of them, and you end up with 2D particle images, and then a typical cryo-EM processing yields a 3-dimensional map like this. And then this is where the new bit starts. So you take all of your 2-dimensional images that contributed to this and are a function of dose, and you create maps of each at each time point, or at each dose point, as it were. So these are the real space maps here in gray. And you can see the radiation damage kicking in here, right? This first map is the best, and it gets worse and worse until a lot of the high resolution features are cooked away. And this is the equivalent Fourier space representation of it. So this is what you see in Fourier space. This is this exponential decay. And you then go in this Fourier space map and fit every single one of these voxels, or these structure factors, individually, and extrapolate them back to 0 dose. And so the final map is just a single map that's calculated from this series of maps. We've done this for several molecules now. I'm just showing a few of them here. This is DPS, this is light harvesting complex 2, this is catalase, and this is apoferritin. Some of these have been published and some of them haven't. But in this case, all of them give this linear fit back to 0 dose, which is what we want to see. So again, every single one of these, the first frame is the best, and it is consistent with our notion of radiation damage, which we measure from X-ray crystallography. This is just an example of one of these we did recently. For the material scientists, who work on photovoltaics, this is the photovoltaic of nature. This is the reaction light harvesting complex that takes photons in through this series of what you can consider antennas. And then that energy gets non-radiatively transferred into the center here to the point at which an electron is separated, and you store it as chemical energy. And of course, this is what nature uses in order to harvest energy from the sun. And it's quite an interesting structure and story, but I won't go into the details. But I will say that, being able to extrapolate these maps down to 0 dose meant that we could really see all of the lipids. We could see the individual reaction sites, the cardiolipins, et cetera, at a level of detail that we couldn't do before. So it was really a lot of fun to do this particular structure. Right, how am I doing on time, Wa? Minute or two. Okay.
Yeah, go ahead. Right.
I'll just quickly mention what we're working on next. So we've been studying the potential of using liquid helium to reduce the radiation damage to specimens more than we get at liquid nitrogen temperatures. We recently published a paper about this, and again, in ultramicroscopy. It's in the current issue, actually, along with 2 other papers on imaging thick specimens. And the potential benefit here is not enormous, but it's significant. It's somewhere between 1.5 and 1.8 times a reduction in the damage to protein specimens at liquid helium temperatures versus liquid nitrogen temperatures. And that will allow us to do even better in terms of this extrapolation back to 0 dose, and be able to determine the structure of molecules that are even smaller than we can do now. So I don't think we want to leave this behind. So that's our next thing. The problem is that, people have been looking at liquid helium for a very long time, and every time anybody's done a comparative study of the resolution or of images, they've found that things are always worse at liquid helium temperatures. This is a very recent one from Werner Kuhlbrandt's lab, where they did apoferritin at liquid nitrogen and liquid helium, and they got basically the same resolution. And the interpretation of this was that the movement was actually worse at 17 Kelvin than at 80 Kelvin, but perhaps the images were better due to a reduction in radiation damage. So you can see, obviously, we're interested in this, because now that we have a proper theory of why specimens move, we have the potential to revisit this and hopefully eliminate the movement of the specimen at liquid helium temperatures as well, and thus unlock the potential improvements at these lower temperatures. And so I'll just show you very briefly an unpublished result so far, and that is imaging gold nanoparticles in small holes, even at about 14 Kelvin liquid helium temperatures, and we see that the movement is actually down below an angstrom. So this is encouraging, but we're not quite to the point where we're ready to collect data sets yet, because you have to understand all these details at low temperatures as well. So anyway, this is going to be fun, and this is a direction we're heading in. Right, I'll stop there and thank lots of the people who are involved in the work, especially Matthew Pete, who's been with me from very early days, and Katerina Naidanova, whose thesis, which incorporated a whole bunch of the stuff I just showed you. She just defended on Friday, so she's now Dr. Naidanova. Very thrilled and happy about that. And Pepe Jai, who's a material scientist who joined me as a postdoc briefly on a fellowship and helped with getting some of our lithography of these small holes going at the beginning. And Jude Short, who's a very experienced senior programmer from the LMB, who's sort of come out of retirement to help with writing a new bit of code for doing these 0 dose extrapolations. Right, I'll stop there and take questions.
Hey, good. Thank you very much, Chris, for these excellent results and extremely convincing data. Okay, his talk is open to questions. Could you type your question in the Q&A? Okay, Chris, there's a questions about how you can estimate the resolutions of the map at the 0 dose.
Well, you can use all of the same tricks and techniques that we use now. So Fourier shell correlation is the traditional method of estimating resolution of an entire map. But of course, that has its drawbacks in the sense that, it's a global resolution that's averaged over all of the structure factors in the map. But essentially, all of the same things apply. Now, we will probably need to have new tricks for preventing people from overfitting or overestimating resolution in dose extrapolated maps. But this certainly can be done using the same sort of statistical techniques that we've used in the past. For example, splitting your data in half and processing them independently, or leaving certain numbers of the structure factors out and making sure that everything makes sense when you put them back in. So these sort of tricks that I think are going to be needed for 0 dose extrapolation as well, but we need to get a handle on quite a few more data sets to understand the statistics and the metrics, to develop them. But there certainly is, nothing special in terms of the ability to measure resolution in the map. FSC is fine.
Great. Okay, so I have a questions about your latest maps of the apoferritins. When you compare the map that you obtain versus those has been published at about equivalent resolutions, do you find any interesting features that the old structure did not display?
Well, yes and no. We haven't ourselves gone to very high resolution, sort of sub 1.5 angstroms in any of our ones, because quite frankly, we just didn't, it wasn't the direction we were interested in heading. We were pretty happy with 2 angstrom resolution in terms of being able to build all the maps. But there certainly is an opportunity there for people who want to push resolution as high as possible. to make comparative studies and see, in particular, I think hydrogens are going to be interesting to look at carefully, but we have not done this yet, no.
Yeah, I think particularly looking at the ions and water will be very interesting in the case of hyperferritin.
I think we certainly see more water molecules in our maps than you see in ones that are done with regular grids, but there's been, we haven't done a quantitative study of any sort of that.
Sounds good. If one has to have a question, if one has to set up to make this gold foil film and the grid you described, usually how long it takes to make a batch? Is it a long process, or once it's set up?
It depends on how you plan your day, as it were. I mean, it's really only a 2 mass step process, so you can do the whole thing in about 2 days. And you can do several wafers in parallel if you wish, because while you're waiting for one step to happen, you can start the next one. And so in a small clean room, you could probably do 3 or 4 wafers in 2 or 3 days, I would say is reasonable. So you could have a few thousand with one person working for 3 days.
Good. Okay. I have another questions about the radiation damage. So in your overall reduction in helium at 1.5 times, do you refer only the high resolution data, or you refer an average data at a broad range of resolutions? I'm pretty sure based on our previous studies, it would be a resolution dependence.
Well, there is a resolution dependence to it, in the sense that, the higher resolutions are certainly fade faster, and they're more easy to measure this radiation protection factor, because, the ones that are fading the fastest show the biggest difference from the protective effects. So, there is certainly that. If you only look at the 9 angstrom information, by 30 electrons per angstrom squared, it's hardly faded over the map, whereas the 2 angstrom information is completely gone. There's nothing left. So and you also have to be a bit careful about measuring individual structure factors too, because some of them may not decay. Some of the structure factors actually go up as you increase the dose. And so what's the explanation for this? Well, it's because while you're breaking all of the bonds and all of the molecules globally, a certain amount of the carbon is still there, and it reforms other bonds, and that actually can strengthen structure factors in certain areas. So it's quite a complicated thing. But over the global maps, we've seen that they all do decay linearly with this B factor, which is a fairly simple model. I mean, you could certainly do more sophisticated modeling of what's going on with the radiation damage, but I think we only just now have this opportunity to start looking at it because we've gotten rid of the movement, because the movement was causing a huge amount of information loss at the beginning, where all of the interesting bits are happening. So we were in doses that were much higher than the crystallographers had been studying radiation damage with. And, and it was always convolved with this blurring effect from movement. So I think there's just a lot of opportunity to study this now, as this technology becomes more widespread. So I'm quite excited to see what folks who are, very interested in the radiation chemistry can do, and in understanding this in more detail as well.
Great. Hi, Peter, you have questions?
Oh, Chris, hi. Thanks for the very nice talk.
Yeah.
I was interested, do you have any idea of what the activation energy is for water diffusing on ice? Because I was thinking about if I understand what you're saying, that bowing that you get is relaxed when the electron beam strikes the ice because of enhanced surface diffusion. So I wondered if you could actually approach that relaxation by maybe heating the sample up a little bit, if people have thought about that. In other words, you would heat up to drive surface diffusion, and then you would cool it back down before you turn the beam on.
Yes, indeed, Peter. I think you're thinking along exactly the right lines. There is an activation energy, and what we've measured, so the number that's been measured reasonably accurately is the average movement of a water molecule per unit of fluence on the specimen. And that turns out to be 1 angstrom per electron per angstrom squared. And so you can turn that into an activation energy. And if you then take that and turn it into a temperature, you find out it's around 160 Kelvin or so. So it's like taking the temperature of the specimen from, say, 80 or 90 Kelvin, which is where it's at, when the beam is off, and instantaneously and locally raising its temperature up to 160 or so Kelvin. And as soon as you turn the beam off, it's instantaneously back again. So I don't really think about it in terms of temperature, but if you were to do it that way, it all is equivalent for sure. And so one thing that people have done is try to plunge at higher temperatures, or to sort of plunge their grid and then raise the temperature up and then lower it back down again. There's one paper studying this, and they did see a reduction in the movement. The trouble is that as soon as you go back down in temperature, you lock it back in again, and then you build up more stress, because it's not, that density change as you go down closer to liquid helium is not flat. So you still build up stress. So in the end, you just don't want it to buckle ever, during the preparation process. That's the best thing to do. And so for that, you just control the geometry, I think, and bring it in through the boundary conditions. So, but yeah, I think, the way you're thinking about it is exactly right.
Thanks. Thank you.
Okay, good. I'd like to thank Chris again and for these stimulating discussions and talks. And now I want to turn the floor back to Bob.
Thank you. And I'm just wondering, Chris, if image drift correction, which is pretty good in the one view camera, I don't think it's been incorporated in the K2 or K3 yet. I wonder if that could improve the situation, or it's not sensitive enough.
Well, we do drift correction, actually, and even in these zero dose ones, we do. The one thing that we can benefit from in the small holes is using the edge of the foil as a reference. So the foil edge itself becomes a fiducial that's extremely easy to track. So you can actually track the edges of the hole, and you can do it to sub-angstrom accuracy in every single frame. So that's actually what we do. We just track the edges of the hole, which are made of gold, and that drift correction eliminates all stage drift or any other sort of weirdness happening from the microscope, or and then you just have the movement of the particles within the hole that's left. And so that is indeed what we do.
Thank you. Okay, I'm going to pass it over to Professor Jen Dion, who is going to introduce our next speaker. Jen.
Great. Thanks so much, Bob. And thanks, Chris, for a really amazing talk that really beautifully bridged techniques both in biology and in material science. It's my pleasure to introduce Professor Peter Crozier from Arizona State University. Peter received his PhD at the University of Glasgow in Scotland, and since then has had over 20 or perhaps more years of experience in developing and deploying some of the most advanced techniques in electron microscopy and spectroscopy. As you'll hear in his talk, he's done some really beautiful and frontier work in using TEM to understand energy materials, especially catalysts and electrolytes. And he's also done a lot of really outstanding work applying electron energy loss spectroscopy to determine the optical and also vibrational properties of materials. Among numerous awards, he is a fellow of the Microscopy Society of America. And in August 2020, as Bob noted earlier, he became the president of MSA after having previously served as the treasurer for over 6 years. So Peter, we're so honored to have you as the president of MSA here at EM-X, and we're looking forward to your presentation. So the floor is yours.
Well, thank you very much, Jennifer, for the very nice introduction, and to Bob and the entire team for the opportunity to present here today. I'm going to sorry, let me just make a couple of optimize for video clip, yeah. What I'm going to discuss today is some of the work that we've been doing. Can you see my slides? Is everything fine?
Yep, it's perfect.
Yep. Some of the work that we've been doing on something that we're calling fluxionality. It's something that we've kind of become interested in the last 2 or 3 years, and it's something that probably all of you have seen before, and it's very much relates to what Chris has just talked about, changes that you see in structure, although we are hoping that most of these fluxionality changes that we see are not induced by the electron beam. And so I'm going to take you through some of the stories about when the structures are changing and whether or not we can extract any information about functionality from that. As Jennifer has mentioned, in my group, we're sort of motivated by energy conversion technologies. We don't make any devices, but we tend to focus on some of the materials functionalities that we think are very interested in investigating. And we're typically working on photocatalytic reactions. So we have programs in water splitting. We're interested in ionics, particularly in oxygen ion conductors for electroceramics. And then, of course, we also work, as Jennifer said, a lot on thermocatalysis. Much of the information that we extract about these materials comes from advanced transmission electron microscopy techniques, and in particular in situ and operando electron microscopy approaches. And so just this cartoon on the left here shows the our idea of what an in situ or operando experiment is. So the idea is that you have some material inside the microscope or the synchrotron. It can be any characterization tool. You apply some stimulus to that, you know, gas, heat, light, and of course, when you apply that stimulus to the material will change in response to that stimulus. And so then you could record images or diffraction patterns or spectra to characterize the change in the material due to that stimuli. And then if you measure some performance, usually some technologically relevant performance functionality, for example, an IV curve or light emission, or in our case today, reaction products, we would call it operando. The microscope that we use to do a lot of our in situ and operando work is this FEI Titan ETEM, and actually it's identical to the microscope that you have at Stanford. You can see here this homemade gas handling system on the left. And of course, it's equipped with various detectors. We're lucky enough to get this Gatan K3 direct electron detector installed in the last year. The advantage of that for in situ work is that you've got almost no readout noise, of course, and readout rates approaching 1,000 frames per second and fairly large areas. Just one thing, I know that many of you are probably familiar with these windowed cell gas or liquid holders. This is, in this ETEM, the chemical reaction cell, if you will, is actually built into the microscope. There's a differential pumping system. So the pressure that you can achieve in this particular type of design is about 15 torr. But even though it's low pressure, it's actually ideal for imaging the surfaces of nanoparticles because you don't have the interference, the additional noise from the window, which, as you'll see for this work on fluxionality, signal to noise is absolutely everything. The way that you would go about doing a typical operando experiment, and there's a paper we just published a year ago here by Ben Miller that goes through a lot of the details of the technique. If you're looking at, say, a reaction, we often look at CO oxidation, and I'm going to show you some work today on CO oxidation of platinum supported on ceria. Typically what you'll do is you'll go to the microscope, find some ideal nanoparticles in favorable zone axis orientations, and then you'll change the reaction conditions to those that are relevant to catalysis and look at what changes occur. So here's just an example here. This would be a platinum nanoparticle oriented along a zone axis, this time in an atmosphere of nitrogen at 20 degrees Celsius. And so you would say, well, this is my perfect initial configuration. And then you would let in the reacting gases. And this is actually very often what happens. So you start off with this perfectly oriented particle, and then when you change to the reaction conditions, the sample tilts or moves, and you can actually see this is exactly the same area. And what you see in the presence of CO and oxygen, that the platinum nanoparticle is no longer stable. And electron microscopists have seen this for years, and we often just say, well, this is not a stable particle, we'll just move on and find one that's stable. Here's just the frame averaged versions of these images. So here's the image in nitrogen, and here's 1 second frame average in CO and oxygen. And so you would say, well, this is no good, I'll just move on. And the reason for the instability, again, related to some of the things that Chris might have talked about, charging, poor contact with the support, electron beam effects. But actually this experiment which Joshua Vincent did was very interesting because if we change the reactant gas, the stability, the particle becomes stable again. So if we pump the CO and oxygen out and go back to vacuum conditions, the particle is stable. And many people that have worked in catalysis for years have often speculated that actually the catalytic functionality is intimately connected to structural reconfiguration on the catalyst, that you can't have reactants being converted to products without some significant structural change in the catalyst. So we were actually interested in the possibility of being able to interpret something like this in a way that might be provide us with some hints as to how the catalyst actually functions. At about the same time, we were working, as I say, we work on oxygen exchange technologies and electroceramics. And so we were looking at oxygen exchange transport through bulk oxygen ceramics and also exchange at the surface. And one of my students, Ethan Lawrence, was trying to look at the defects on the surface of cerium oxide. So this is an image of cerium oxide. The bright, it's a negative CS image in the Titan. So the bright features, these very bright dots that you see here are the cerium atoms. And then you can just see the oxygen atoms. They're a little bit fainter to see, but the oxygens are present, and you can even see the oxygens up at the surface here. So this is, it's very, very nice in that way. What was interesting was that the defects, in this case, the steps that we were interested in, always looked fuzzy. And again, electron microscopists have often seen this before, where you'll say, well, jumping around, or it's out of focus, or there's all sorts. We've all seen it, and we just kind of ignore it and look for a region of the sample that's stable. But with the direct electron detectors, this is a 1 second exposure. With the direct electron detectors, we can start to run the sensor at higher readout rates. This is 40 frames per second. 5,000 electrons per angstrom squared per second, which is actually below the critical dose, which Bob Sinclair and his group determined for Syria at Stanford of about 7,000 or 8,000. And what you see is that even though the image is clearly noisy, this is individual frames, the fuzzy Syria atom column that you see here is actually moving around. So it's moving back and forward. And actually, when Chris was talking, I realized, if I show a molecular biologist 5,000 electrons per angstrom squared, they'll just immediately claim that this is all radiation damage. Ethan did check this. It makes no difference all the way down to 50 angstroms per 50 electrons per angstrom squared per second. So that instability that you see is not primarily caused by the electron beam. And we did some molecular statics because we know that, of course, Syria is ionically bonded, and this is just a cartoon of a surface. The cerium atoms are shown as red, and the oxygens are red and the Syrias are blue. And what my student Tara Boland did was she just pulled an oxygen out of the surface. So she created an oxygen vacancy. And of course, because of the ionic bonding, when you pull that oxygen out, the structure relaxes. And so she did that for a step and then used the molecular dynamics models to simulate the TEM images. And this is what the simulated movie of creating and annihilating an oxygen vacancy looks like in the microscope. And in fact, we realized that if you think about this, here's, of course, this is going on very quickly. This is probably, hundreds of femtoseconds is the time resolution for the molecular dynamics simulations. And so if we were to image this, we would have a superposition of these kind of images. And I always, to try and explain this, if you think of a fast car moving forward and you take a photograph with a long exposure time, the car, of course, looks blurred or diffuse relative to the background, but of course, you still know that it's a moving car. And so the interpretation that led us to for these fuzzy atomic columns at the step is that, in fact, the reason they look fuzzy is because they're dynamic. They're moving back and forward during the exposure time, and that's causing this fuzziness that we see. And what's interesting about this is that we're getting information, very highly localized information at the atomic level about structural dynamics, okay? But we don't need high time resolution to see it. So we can measure the magnitude of the structural distortion that's associated with the structural dynamics without necessarily having ultra fast. We don't need to have picosecond time resolutions to see it. So Ethan Lawrence and Barnaby Levin went and decided to analyze the mean cation displacements from these movies, and the error, the uncertainty in the measurement here is about 5 picometers. And so what they've done is they've measured as a function of time the displacement of these cation columns as a function of position along the Sirius surface here. And what you see is that the step edges are indeed much more mobile. The displacements on the order, or the means displacements are on the order of 25 picometers. But there's lots of other interesting things. For example, if you look carefully at this terrace here, this terrace is actually buckled, and you can see that there are pretty high displacements taking place on this buckled terrace, which would again be indicative of oxygen vacancy creation and annihilation. And in fact, if you go to the density functional theory, you find that the oxygen vacancy formation energy on a 1,1,0 surface is actually much smaller than the vacancy creation energy on this 1,1,1 surface, which is predominantly what we have here. And so we went over and looked at a 1,1,0 surface, and here's the movie, and you can see that along the surface, all the cation columns look fuzzy. And Ethan and Barnaby measured that, and what you find is that there's very large activity going on here. The cations are very active, and of course, the more active the cations are, that's indicative of the active site for creation and annihilation of oxygen vacancies. And in fact, because we have these direct electron detectors, even though we don't necessarily, we can sense structural dynamics without needing high time resolution. Of course, we can take advantage of the time resolution that we have. And what they've done here is they've simply counted the displacements of the cation in each frame of the movie. And so what you're looking at now, the coloration that you see now is the displacement frequency, how many times the cation moves per second, which is indicative of the creation and annihilation of oxygen vacancies. And again, you see a similar kind of behavior here. The 1,1,0 surface is much more active than the 1,1,1 surface, and the defects on the surfaces are much more active than the perfectly unstrained terraces. And you can take that further. You can actually go ahead and calculate activation energies. If you just assume simple Arrhenius relationships here, you can go ahead and you can determine the activation energy for oxygen vacancy creation and annihilation at different sites on the surface. And typically in these experiments, we see changes on the order of 0.10 electron volts, which, remember, even though that might sound like a small number, that translates into factors of 20 or more differences in the activity of those sites for oxygen exchange at the surface. And so we just published this last year in ACS Nano. If you're interested, you can take a look at some of the details. So that was telling us that these fluxional behaviors that we're seeing can actually be, they're very interesting. They tell us where the active sites are for the surface, and we can, and if we analyze them carefully, we can actually start to quantify the differences in activity between different sites on the surface. And so it made us think a lot more about systems that function through structural dynamics. And of course, just to connect back to some of the things that Chris was talking about, if you think of something like a catalyst, an enzyme, these are molecular dynamics simulations from my friend Mahmoud Maradi at the University of Arkansas. And of course, the fluxionality that you see here is absolutely part of the chemical conversion process. The enzyme only functions as a catalyst when the enzyme is undergoing these conformational changes. And of course, there's a lot of work being done to try and understand these conformations and the different states of the enzyme. And of course, the same thing probably is going to happen in a materials-based catalyst. So here is platinum nanoparticles, just one layer of platinum. I'm sorry, you might not be able to see it so clearly, conducted by our collaborators Byung-Kum and Chang Zhu at the University of Nevada, Las Vegas. And what they've done is they've just put carbon monoxide over the surface of the platinum. And you can see, obviously, there's a lot of jiggling around going on here. And if you look down here, you'll see the CO starting to almost bond with the oxygen and pull it out. We're almost at the transition state there. But I remember Byung-Kun was so excited about this because this molecular ab initio of molecular dynamics movie was almost 2 picoseconds long. And so, of course, I'm thinking that we have our fabulous new direct electron detectors, but their typical temporal resolutions 10 to the minus 2 to 10 to the minus 3. So the question is, how do we bridge this temporal gap? And so we thought a lot about this. And even though the elementary steps involved in a chemical or transport reaction are very fast, things are actually slowed down because of the energy landscape. So if you think of a process going on in a material, you can think of a series of metastable states associated with a transition. What we're showing here is a CO, elementary steps in CO oxidation reaction. So the CO goes down, and these yellow and orange circles represent the strain that's induced in the surface of the catalyst. But it doesn't really matter what the process is. The point is whether I'm talking about a chemical reaction on a surface or oxygen transport through a material. There are going to be these metastable states as the system evolves. And we can think of the energy landscape associated with each one of these metastable states, which we've just labeled M1, M2, and M3 and M4 here. And the energy landscape, of course, these metastable states are separated from each other by activation energies. And if you look at typical values of activation energies and you look at typical jump rates here, what you see is that, for example, if you have an activation energy of about 0.6 eV, at room temperature, the fastest jump rate would be 1,000 jumps per second. If you go to 0.7 EV, we're down to 18 jumps per second. So actually, the system's going to be, these activation energy barriers are going to slow down the transition between different metastable states. And so if you think about what you might see in an electron microscope, you're going to see time sequences between the longer-lived metastable states. Of course, the system can jump forward and backwards depending on how symmetric or asymmetric and how high the activation energy is. So you'll probably see a superposition of the metastable states, for example, M1 and M2. This is what we saw in the Ceria. We saw a superposition on the longer exposure of the Ceria atom in 2 different configurations. And then, of course, the lifetimes of these metastable states will depend on the activation energies between neighboring states and of course, the temperature. So now we can think, if we now think about structural dynamics or what we call fluxionality in terms of transitions between metastable states, and that the TEM image is going to show us the longer lived states or superpositions of states, we can go back to this platinum nanoparticle that I showed you early on and say, well, can we interpret this movie in terms of a superposition of different structures? And we had a clever undergraduate in the group at the time, Claire Block, and she was very interested in investigating this. And so we gave her some of the simpler frames from this movie, some of which you can see the evidence for a twin plane. And what Claire did was she simply went through a series of rigid body rotations. I calculated the images for different rigid body rotations and then superimposed them together and added some noise. And here's what she got. The right hand is Claire's simulation of a superposition of different metastable states. And the left hand is one of the frames from this crazy movie over here. And even though they don't match exactly, but certainly it tells us that this idea of observing superpositions of different configurations is probably the correct interpretation. And if she had worked a little bit harder, she might have been able to get a better fit. So we can just to summarize what we mean by fluxionality, it's, if you will, kinetic pathways, meaning the transitions between different metastable states in the system. It's associated with electron transfer. So what we typically see is bond length changes, strain, or bond making and bond breaking. of course, is stochastic in character, but generally shaped by the energy landscape. And of course, the processes that we're looking at are reversible. And so you can imagine things jumping forward and backwards. And so we get a superposition. And here's just another example from Tara Boland. She's looking at transport of oxygen. Again, this is oxygen transport in Syria. And here's the structure as she does this NEB calculation with DFT. And here's the energy landscape. She calculates an activation energy barrier of about 0.8 EV, which is about the right value, matches experiments. And so you could say that when the oxygen is in the left-hand side, that would correspond to structure M1. And when the oxygen is in the right-hand side, that would correspond to structure M2. And if you look at the local strain field associated with M1 and M2, they're different. So in principle, you would be able to differentiate the oxygen in those two different sites by characterizing the strain of the initial and final metastable states. So even though we're using it mostly for catalysis, of course, it would apply to transport. So for example, bulk transport, ionic transport, what I'm showing you with the DFT simulations, things like polar on hopping, interface migration, nucleation and growth, and then of course on surfaces, things like catalysis, surface diffusion and surface phase changes. So this is what we're calling fluxionality. And we think that in the electron microscope, we can actually measure this. So I want to just show you an example of using it to go a little bit deeper into the process of CO oxidation over platinum supported catalysts. And this is where there's complicated surface and interface interactions. And Joshua Vincent was working in this project. So just a little bit of background on the system. Here's a platinum nanoparticle on a cerium oxide support. In CO oxidation, the carbon monoxide chemisorbs onto the platinum with the carbon side down. The CO then migrates down to the metal ceramic interface, and the CO plucks an oxygen out of the oxide, creating an oxygen vacancy to produce a CO2 molecule. And then those oxygen vacancies are subsequently backfilled through the dissociation of molecular oxygen. So Josh was studying this. He made lots of different catalysts, and we characterized them in the reactors in the lab. And I want to just show you what he saw when he did operando experiments in the electron microscope. There's a lot in this slide here. And we actually measure chemical kinetics quantitatively inside the ETEM. And I don't have time to talk about how we do that. It involves using electron energy loss spectroscopy and also a lot of finite element analysis of heat and mass transport. If you're interested, we published the process in this ultra microscopy paper here. But what I want you to look at is, here are platinum nanoparticles, and here's the Syria support. In the nanoparticle, the platinum atoms are in black dot focus, the Syria is in white dot focus. And initially, the conversion of CO is at 0 at 144 degrees. And as we increase the temperature, because we can measure kinetics quantitatively, we can determine what the conversion is, about 20%. And from quantitative chemical analysis, we can convert that conversion into turnover frequencies. So the turnover frequency is 0 at 144 degrees, and it's about 1 per site at 285 degrees. And what I want you to notice is the difference in the appearance of the catalyst when the catalyst is active and when the catalyst is not active. And of course, you see immediately this blurring of the surface atoms of the Syria, which we now know is associated with oxygen vacancy creation and annihilation. And you also will see now blurring of the platinum nanoparticles here. You can see that in these images on the right-hand side, it's hard to see the lattice fringes, and that's because these particles are undergoing the kind of dynamic fluctuation that I showed you before. I should point out that this was not done with a direct electron detector. This was an old multi-scan camera that Josh did this at the time, and so we don't really have the luxury of going to very high time resolutions, but the time exposures are quite long. But this is a wee bit like the analogy that I showed you about the moving car. Even though we don't have good time resolution here, we can see the magnitude of the structural dynamics is clearly much greater here than it is here. So Josh went and processed these, and again, I won't go through the details here. He used Fourier techniques to measure the dynamics on the platinum nanoparticles and found that they became more dynamic as the turnover frequency increased. So there was a definite correlation between dynamics in the platinum nanoparticle and catalytic activity for CO oxidation. And then he also quantified by measuring the visibility of the fringes associated with the ceria at the surface here. And he was able to show that that visibility also correlates directly with catalytic turnover frequency. So what he's got now is that these fluxional behaviors that we're seeing at the surface of the ceria and on the platinum nanoparticles directly correlates with the catalytic functionality that we're interested in. And there was also an outward relaxation that he measured of about 15 picometers here, which is also associated with turnover frequency. So I think what we're getting from this is actually it's summarized in this slide here, which I probably don't want to go into in a lot of detail in the interest of time, but essentially what we're finding is that excuse me, sorry, let's just go back here. What we're finding is that the fluctionality that we're observing in this case associated with reconfiguration of the platinum nanoparticle and the distortions that are taking place on this area are all correlated with the catalytic activity. And in fact, it's the creation and annihilation of those oxygen vacancies. What that's doing is it's degluing or it's debonding the platinum nanoparticle from the surface of the ceria, which is leading to this rapid reconfiguration of the platinum nanoparticle. And the creation and annihilation of oxygen vacancies, which is associated with this so-called Mars-Van Crevelen mechanism of CO oxidation, is what's leading to the streaking of the top layer of cations on the surface here. And if you actually measure the strain here, if you measure what we call the fluxional strain, it's approximately 34%, which is very, very large. And so the oxygen reduction reaction for the CO oxidation is actually taking place on these highly distorted and highly active ceria nanofacets located between the two platinum particles, and then the oxygen is being transported to the interface for the CO oxidation. So if you're interested in more of the details of this, we published this last year in this paper in Nature Communications. In the last few minutes, I just want to quickly talk more generally about something that we've been trying to work on in the last few years, which is trying to come up with descriptors for this fluxionality. And it's a very complicated topic and one that we certainly haven't come to any conclusions about, but I just want to, in a couple of minutes at a rather superficial level, just show you some of the ways that we can approach this. And I'm going to do this in the context of cation migration, again on ceria. And at this point, we simply increased the electron dose. We know that high electron doses will reduce ceria. So we've turned the electron dose up to 100,000 electrons per angstroms per second. Chris is probably gasping in horror at this, but that means we can run the sensor at 400 frames per second. So each image is 2.5 milliseconds. So we generate lots of frames. And because we're increasing the concentration of oxygen vacancies, we destabilize the cation sublattice. And so you can see a lot of migration of the cations back and forward. And we wanted a system like this so that we could start trying to understand this. Here's what one of those 2.5 millisecond exposure images looks like. So it's pretty bad. It's a little bit similar to what the problem in cryomicroscopy. We're running the sensor faster and faster. And of course, the faster we run the sensor, the lower the number of electrons per image. And of course, there's an inverse relationship between temporal resolution and spatial precision. If you want to get high spatial precision, you need to frame average. If you want to have high temporal resolution, you can't frame average, but it will be much more difficult to determine the position of the atomic columns. So we are, looking at a lot of different approaches to handle this question. Again, I won't talk about these in detail. Denoising is important, and our approach to denoising with neural networks, both supervised and unsupervised. Some of the work is published last year in this microscopy and microanalysis paper. Blob detection, if you want to know the positions of the atomic columns in very noisy data sets, we've actually found that this blob detection approach from computer vision seems to be more stable than Gaussian peak fitting, and we just published that a few weeks ago. And then we're using other techniques, semantic segmentation, neural networks, hidden Markov models, topological analysis, etc. But I just want to show you a little bit of how we can proceed here. So Ethan Lawrence was measuring the intensity of different atomic columns in these images, for example, atomic column 1 here, and he's showing you how the intensity varies as a function of time. And he did a very nice investigation of the fluctuations of these two columns. It took him a long time to measure them all and convert the intensities using simulations to the number of atoms in the column. That's great, but of course, we have to think about the high level interpretations. And in fact, I always think about molecular biologists who think of structures in terms of molecular motifs. So in material science, we want to know where each atom is located as a function of time, but that's really just the beginning of the story. That's like me telling you where every letter is located in a novel. It's not necessarily the same as me telling you what the words and sentences or paragraphs are. And so the higher level information is actually associated with trying to describe the dynamics in terms of metastable states. And Ramon Manzoro has been working on this. Here's examples of two different ways of classifying metastable states. In this one, these two states are differentiated through strain. So if you look at the separation between these two atomic columns, it's 5 angstroms in this case and 3.5 angstroms in this case here. So those two states are differentiated through strain, whereas these 4 states down here are differentiated through atomic migration. So there's an atom here which has migrated away, and you can see that the positions of the atomic columns are actually different here because we've got surface migration going on here. So Ramon has been trying to analyze this in some sort of logical way. He's come up with this simple binary descriptor of these metastable states where he uses blob detection to measure the occupancy of each one of these columns. And if the column is occupied, it gets labeled as binary 1. If the column is unoccupied, it gets labeled as binary 2. And he does that for all these columns, 1 through, in this case, it would be 1 through 26. And so each state is then associated with a stream of binary numbers. And here's what these different states look like. And then he can take his videos, which have 9 and 10,000 frames, and he can then analyze using blob detection. He can figure out which metastable states are present or most likely to be present in each 2.5 millisecond frame. And so here now what I'm showing you is just the presence of a particular state as a function of time here. So this is structure 3 and structure 6, and you can see that different metastable states come and go at different times during the movie. And of course, we're trying to understand the interpretation of these metastable states in terms of energetics. And we think that we can interpret the energetics of these states in terms of the coordination of oxygen, whether or not there are oxygen vacancies present or not, because when there are many oxygen vacancies present, that will lower the coordination around this area and increase the probability of migration. So one way that you can explore that is by looking at the transitions between metastable states. And Ramon has done that. So here's a cartoon representation. If I'm in state 1, what's the probability of the next state being state 2 or 3 or 4 or 5? And so you can see there are all these possible transitions. And if you have enough data, you can start to define transition matrix probabilities. And here's, I'll just finish with this. Here's an example of one of these transition matrices that Ramon has defined, where each matrix element is the transition probability between one metastable state and the other. And just for ease of viewing, we colored the high transition probabilities green and the low transition probabilities red. And so if you look at the green column here, this is all associated with transitions into structure 1, and structure 1 is what we might call the ground state. So everything likes to transition into structure 1. Whereas if you look at these columns over here, transitions into structures 6 through 9 are much less likely, and that's because they actually involve these add atoms. So Ramon is trying to relate this to these kind of transition matrices to kinetics and statistical mechanics, and he's working on a manuscript right now. So I know I probably have run out of time, so let me just summarize by saying that these spatio-temporal structural dynamics can be detected with microscopes right now, and especially these direct electron detectors really enhance their ability to do this. What we see at the atomic level is the longer-lived metastable states or superpositions of those longer-lived metastable states. With the new detectors, in principle, we can go to 1,000 frames per second. I have to tell you that when we run the sensors at those speeds, noise, signal to noise is a big issue. So we have to think very, very carefully about how we can interpret what we can actually get from images running at 1,000 frames per second. But definitely this fluxional behavior can be linked with functionality. We need to develop more sophisticated data processing processes in order to quantify the fluxionality, but I think I'm pretty convinced that we'll be able to do very detailed atomic level fluxionality and functionality over the next few years. And I just want to thank you for your attention. This is Tara Boland that did a lot of the DFT and MD. Here's Ramon that's been doing the transition matrix element, Ethan Lawrence and Joshua Vincent and Barnaby Levin that did a lot of the work here and funding from NSF and DOE. Thank you very much.
Thank you, Peter. That was an incredible presentation. I'll hand over most of the Q&A for Bob, since I have to run to give a seminar at 9:30. But I wanted to ask a quick question on the time resolution that I think was also brought up in the Q&A. Apart from being limited from the detector resolution, say to 1 millisecond, do you think there's a way you could implement some sort of a stroboscopic imaging where you can have, say, like an input that causes a fluxional behavior and then
I absolutely think you could do that. You could certainly, the idea would, if you were sure that your process was repeatable, you could stroboscopically stimulate it, say 1,000 times, synchronize the detector, and then you could simply frame average at the same symmetrically equivalent point in time in order to see what's going on. So absolutely, I think that's something that's possible to do. Yep.
Cool. Thanks so much. Bob, I'll hand it over to you.
Okay. Thank you, Jen. Thanks a lot, and good luck with your seminar.
Thanks, Jen. Thank you. Bye.
Thank you.
Wonderful presentation, as always, Peter. Fantastic. As you know, doing in situ experiments, you can't do everything at the same time. But
right.
Going back to the surface, did you do any EELs on the surface of the Sirio? Because I think we found that it was the ionization state changed at the surface compared to the bulk in thin film.
Yeah, so I think definitely you can reduce the surface very, very easily, as you know. And so what's interesting is that the radiation damage will certainly be more pronounced at the surface than in the bulk, because of course there's no diffusion. If you kick the oxygen off the surface, it will be gone. It immediately it's gone into the vacuum. What's interesting, I have a slide actually. I took the slide out, but it's very interesting, the question of radiation damage. The radiolytic and ionization damage doesn't have a strong temperature dependence, whereas thermal processes have this Arrhenius exponential dependence on temperature. So one way that you can differentiate between electron beam effects and true thermal effects, which is what we're interested in, is by varying the temperature. And what happens is, if I think about, say, oxygen vacancy creation, I can create an oxygen vacancy on the surface of Sirio with the electron beam. I can also create an oxygen vacancy thermally by, and if I want to measure the rate of oxygen vacancy creation, if I want to increase the rate of oxygen vacancy creation, I can simply increase the temperature. When I increase the temperature, the radiation damage doesn't change by very much, but the thermal processes change exponentially. So I have a slide that maybe I can show you where we've analyzed that. So in terms of doing the eels, we haven't done eels on these particular materials, but I'm pretty sure that if we did do eels with a STEM probe, we would find that the surface of the cilia is reduced much more rapidly than the bulk. Is that your question? I'm not sure.
It is, yeah.
Yeah.
From the Q&A, there's a question: how do you know that those surface atoms are single atoms?
Well, they're not. No, actually I would suggest that you go to the ACS Nano paper. Actually, Tara Boland, we did a lot of details. We know roughly how many atoms are in the column. So typically on the surfaces that I was showing you, there's something between 3 and 6 atoms in each one of those columns. And so you can then simulate using DFT and molecular dynamics. You can look at what happens if you pull 1 oxygen out from the column or 2 oxygens out from the column. And it turns out that if you have a column of 5 series and you create 1 oxygen vacancy, you actually see the whole column moving. It's actually very interesting. And the phase contrast image, remember, in phase contrast imaging, the position of the atomic column may or may not be the projected potential position. And so what happens is when you pull that oxygen out of the cilia column, the column moves. And whether you pull 1 oxygen vacancy out or 2 oxygen vacancies out determines how much the column moves by, but it typically will move by between 10 and 20 picometers. So even though we have a column of series there, we can still count the number of oxygen vacancy creation and annihilation events.
What's your feeling, Peter, about use of STEM in situ versus TEM in situ?
So the advantage of, so I need to be careful here. And of course, I'm a STEM guy. In principle, high angle annular dark field STEM gives an image that's more simple to interpret. However, remember, if you have strain in a sample, that's going to affect the high angle annular dark field image. So strain, it's not as if it really, it's approximately Z contrast, but only under idealized conditions. So that my first comment is that I think you'll need to simulate, even if you do high angle angular dark field imaging, to correctly interpret what you're seeing, you still need to do simulations. The other issue with STEM at the moment is if you think of these new direct electron detectors with our K3 camera, we can read out the sensor at 1,000 frames per second, and we have a field of view that's 3,500 by 3,500 pixels. If you wanted to do similar temporal resolution with a STEM, you would need to have dwell times on the order of 10 to the minus 9 to 10 to the minus 10 of a second. And there is no STEM system that can read out at that rate. So now you might say, well, I'll just scan over a much smaller area. Those of you that do in situ know that when you're doing an in situ experiment, you never really know where the interesting changes are going to take place. So the large field of view from a practical point of view actually is very, very important. So I would love to be able to do all of this with 4D STEM, and I hope I can do one day in the future. But at the moment, there simply is not the technology to do readout rates at 10 to the at a nanosecond. So I think we're stuck with broad beam techniques for the moment.
Well, I wouldn't say stuck with, but I would certainly
not stuck with.
add that that's why we haven't seen an impressive in situ STEM movie comparable with what you showed today on the regular TEM.
Yeah.
Well, I think we need to wrap up the formal session. So I think I want to thank Ziwen and Raphael for just running the show so expertly and so many times now without a glitch, as far as I understand. I'd like to thank Peter and Chris for just wonderful talks. Wah, do you have anything to add?
Oh, I think this is very stimulating from both your talks. I can see certain commonalities that the material science can meet with the biologies in many different ways, both the spatial and temporal scale. So I'm actually very excited, because among the biologies, we also do molecular dynamics of how the molecule moves. And so I think now listening to Chris talk, then things are even more complicated because many things move at the very beginning. What we see is the end products. So I think will be really fascinating to move the data back to the zero dose, and also to minimize as much as we can to see what goes on, because it's hard to distinguish whether the molecule do or we introduce the movement to the molecule. That's we want to be sure we are not generating artifacts. I'm sure we do generate some artifact, but to what approximation we don't get caught.
Yeah, and to add to that, I'm sure Peter is as well, that we're working on ceria or silicon or something like that, which is much more benign to the electron beam, even though they're a bit sensitive. Right, Peter?
Yeah, and actually I noticed that Nestor had a comment about annealing out the damage in materials. Sometimes the damage is less apparent by heating the sample up because you repair the damage. It's almost counterintuitive, I think, sometimes, but there's quite a lot of work, especially in oxides, where the system is more stable at elevated temperature than at room temperature.
I have a question for Peter. In your situation, does it make any difference in terms of the dose range you give to your specimens? Because the dose range may have a consequence on the heating effect.
Yeah, so I think usually when we're doing, if I take, for example, the CO oxidation example that I showed, we were heating the sample to say 200 to 250 degrees Celsius. So what happens is, in fact, there's a slide that maybe I wanted to share this slide, maybe since some of you are staying on, and actually, this is the slide that I wanted. Can you see this slide?
Yes.
So this is very crude calculation, but this is for an electron flux of 5,000 electrons per second. And we're asking the question, it goes back to Bob's question about, does the electron beam create an oxygen vacancy? So if you think that the vacancy formation, the activation energy for creating an oxygen vacancy is EA, we can calculate the probability, the cross-section for the electron transferring energy EA through a knock-on process or through a radiolytic process. So all the equations are in the literature. So what we're doing here is we're calculating the knock-on, the number of oxygen vacancies created through knock-on, and the number of oxygen vacancies created through radiolysis. And so we're plotting that on this graph over here, but we're keeping the electron dose fixed, and we're plotting the number of vacancies created by knock-on or radiolysis as a function of the vacancy creation energy. In other words, we're letting EA be a variable, and this is these are the two graphs that you see here. And so, so you can see that there's not a strong dependence on the number of oxygen vacancies created, or they only vary by a factor of 10, depending on what the oxygen vacancy formation energy is. Now, if you go to the thermal processes, for the thermal process, the number of vacancies created depends on this Arrhenius expression here. I'm sorry, maybe you can't see this. It's EA, so it's E to the minus E over KT. So that has a much stronger dependence on the activation energy. So that's what this green curve is here. At this one, in this case, it's evaluated at room temperature. So you can see that as the vacancy formation energy decreases, you see this enormous increase in the number of oxygen vacancies created. The reason that's important for us is that we know the vacancy creation energy varies from one site on the surface to the other. So the most active sites are going to be associated with the smallest values of EA. And so that's going to have and the other thing that this graph shows is if I heat the sample up to 600 degrees, what you see is that all of the vacancy creation and annihilation, all of the dynamics in this case that we see is completely dominated by thermal effects. because of this Arrhenius dependence here. So I think that for a lot of the in situ experiments that we're doing, we have to pay attention to electron beam effects, but we also have to remember that many of the thermal processes we're looking at follow this Arrhenius relationship, and that Arrhenius relationship has an exponential dependence on temperature. And so very often, even though we might have some residual radiation effects, when you start to heat the sample up, a lot of the dynamics that we observe is dominated by thermal effects.
Okay, I think we can stop the formal recording now. And I'm wondering, I see Nestor online. Do you have any questions for Chris at all, Nestor?